Now we're going to continue sizing conductors based upon the types of loads, including motors. Now, the figure that we're going to look here is basically our figure 18-12 in the Stallcup's Electrical Design book, chapter 18. And notice now the loads that'll be on this feeder is a 5 horsepower motor, single phase, 230 volt. Then we have receptacles, plugs that you see there. The load's already been calculated in accordance with Article 220. We pick up a continuous appliance load, means that it'll operate for 3 hours or more. We select the largest motor, which would be the 5 horse that we just looked at. We also have lighting loads here that would be on the system. We have 40 amps of continuous lighting load, and then we have a heating load that is larger than the AC load at 5 kVA. So the 10 kW is larger, so we drop the AC load in accordance with the Article 220. And then, of course, we have a single-phase motor, 1 horse, and a single-phase motor, 2 horse, all on a 120 volt supply. So now these are the loads that are involved that this feeder has to supply over to the sub panel that you see there. Now, based upon what we've just looked at, we're going to look at the calculations here and calculate these loads. Now, the first thing is sizing the overcurrent device based upon the loads. So the lighting load at 40 amps is taken at 125%, which would be 50 amps. The receptacle load is not used continuous, so it's 37.5, already calculated in accordance with the rules of Article 220. The appliance load, though, is continuous, operating for 3 hours or more, so at 125%, 37.5. The heating load is used and the air conditioning load is dropped, so we take 10 kW times 1,000 divided by the voltage, 240, we come up with 42 amps. The motor load, then the 5 horse is 28 amps, so it's 100% at 28 amps. The 1 horse is 16 amps at 100%, 16 amps, but the largest motor will be figured later. The 2 horse is 24 amps at 100%. And then the largest motor is that 5 horse, and we just take it at 25%. Or you could have took the 5 horse at 28 amps times 125%, your choice. But just to make sure we only figure it one time, we just took it at 25%, 7 amp. And then notice when we total it, that comes up to 242 amps. Now, 215.3 of the NEC says that the conductor is brought along with the overcurrent device. So table 240.4G, we use that table because we have motor loads involved. And we'll talk more about that table in upcoming illustrations. 430.63 is used because we have combination loads. So 242 amps is 250 amps. So the overcurrent device here, based upon the loads, is 250 amps, as you see in the solution. Now sizing the overcurrent device based upon the motor load. Step 1, then of course we're applying the sections you see listed under step 1. So the 5 horse is 28 amps at 250%. Now we'll get into sizing, but basically speaking, an inverse time circuit breaker under most conditions from your table 430.52 and section 430.52C is 250%. So 250% of 28 is 70 amps, and that is a standard device now, size, from table 240.6A. The 1 horse is 16 amps at 100%. The 24 amp 2 horse is at 100%. So when we total all that up and bring it down, we have to add that to step 2. So the lighting load is 50 amps brought over from step 1 in the illustration to calculation to the left for the lighting load. The receptacle load is brought over at 100%. The appliance load is brought over at 125%. And the heating load is brought over at 42 amps as calculated in the left-hand side of the illustration where the calculations are shown. Step 3, sizing the overcurrent device then, based upon the largest motor in step 1, 250% of the 28 amp 5 horse motor. We come up then, now remember in step 2, 277 amps, in 430.62a, there's not an exception to let you round that up to 300, so we round down to 250. So notice, sizing the overcurrent device based upon loads is 250, but sizing the overcurrent device based upon the motor load is also 250. And as the note points out, in most all cases, these calculations will be the same and provide the same size overcurrent device. But if you had an unusual large motor instead of that 5 horse in step 1, then the overcurrent device based upon the motor load may provide a larger overcurrent device, as we will see in later calculations. Now, sizing the conductors, we've already done that in step 1 and step 2. And notice we come up with a 250 kc mil conductor based upon 242, and we raise that up to a 250 amp circuit breaker. Now going over and sizing the neutral, everything is taken at 100% instead of the largest motor. So the lighting load, no, we're not applying the 125% 40 amps. And notice in 220.61 now that's allowed, not required. It'd be permissible if the engineer won't take 40 amps at 125%. But it's based upon the concept that the conductors connect to a bus. You're not trying to trip that bus bar. You're just trying to not overheat it. So that's the reason the 100% rule will comply with 366.23a as an apple for sizing that bus bar for continuous duty. The receptacle load's at 100%, 37.5. The appliance load at 30 amps, 100%. The motors are all taken at 100%. But notice the largest motor is still figured in at 25%. So we would take the 24 amp motor now value based upon that motor at 6 amps instead of the 28 amps, and we'd come up with 153.5 because it's the neutral loaded largest motor, not the phase-to-phase. And you know, phase-to-phase loads never see neutral loads, not trying to be too awful simple. But 153.5 then, after the golden rule of 310.14A3 informational notes, and table 310.16, the 153.5 requires a 2-alt after the calculated neutral load has been performed in step 1. So we could take a 100% rating and come up with a 2-alt. Well, we might have to use a 2-alt if we use the 125% rule, and in some cases maybe even a 3-alt. So engineers have a choice here. As the note says, in some states, counties, and cities, the authority having jurisdiction may require the continuous load rule to be applied. So continuous loads would be multiplied by 125% if there was an electrical ordinance amendment to 220.61, or otherwise it's strictly up to the designing engineer to design the size neutral based upon 100% loading in accordance with the approval of the authority having jurisdiction based upon the state, county, or city electrical ordinance if they have an amendment to the National Electrical Code.